So without a further delay, let's now continue our discussion. So do you guys have a question or clarification so far before we will start? No? So let me just check whether you guys are already there or not yet. So Mr. Pacific, are you there? Mr.
Yes,
Pacific?
sir.
All right. How about Mr. Barasi?
Yes, sir.
Okay. Mr. Dumondon?
Yes, sir.
And then Mr. Gulaidan? Okay. And Miss Realin?
Present, sir.
Okay, Mr. Eda? Mr. Eda? All right, maybe he went somewhere. Mr. Ray Vincent?
Yes, sir.
Okay, Mr. Jurgen?
Yes po, yes po.
Mr. Reister?
Present, sir.
Mr. Zambrano?
Present.
Okay, Mr. Brian? All right. Okay, so just wait a second. Let me just close the door. What's that? All right. So let's now continue our discussion. So can you guys see my screen now?
Yes, sir.
Okay, so as I'm saying a while ago, this one is a voltage regulator wherein our Zener diode now is in a parallel connection. Okay, so let me just explain or say those this one acronyms RS, VC, VIN. So what are those? So VIN or VS is our voltage input or the voltage source. And then RS here is the series resistance. And then IS here is the current resistance or series current. Okay. And then VZ is the Zener voltage. Okay. And then IZ is the Zener current. RL here is the load resistance or load resistor. And then IL here is the load current. Okay. And then lastly is the VO, okay, which is the voltage output. Okay. So I don't know if you guys can hear the announcement. Suddenly the barangay Kagawads is announcing something, blah 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 about the COVID. Anyway, I hope it's not distracting you guys, if ever that you guys can hear that one. All right. So talking about the formulas, okay. So we have the VTH, IL, IS, and then the PZ. Okay. Is it IS? Yeah, IS. All right. So if you're going to take a look on this one, we have a condition before proceeding in solving for those certain missing variables. So first, you have to check whether it's operating under breakdown voltage. Okay, wherein if VTH is greater than VZ. So why VTH? Because we have to, consider the RS and then the RL in this circuit now. Okay, so it's like, as you can see, this one is actually like a voltage divider, wherein we have the formula voltage source times the R sub L, which is this one, divided by RL plus RS. Okay, so this one is similar with the voltage divider formula. Okay, so we have this is one to check what is the voltage or the Thevenin's voltage at this point. Okay, because let's say if we have 15 volts, so this one will become lesser because we have to detect the voltage drop in our series resistance and then the load resistance. Okay, so that 15 volts will become maybe 12 volts, 13 volts, or even 10 volts. So depending on their corresponding resistance. Okay, so you have to do this one. This is the very first thing that you have to do. So check whether the VTH is greater than VZ. So if our Thevenin's voltage is greater than the Zener voltage, which is a breakdown voltage, okay, then that's the right time that we can calculate for the I sub L, I sub S, and then the power of the Zener voltage. Okay, so PZ here is the power. Okay, all right. So for I sub L, we calculate this current here with the voltage of the load resistor, wherein if you're going to take a look at this one, the voltage of the load resistor is same with the VZ. Okay, because whatever passes or whatever is the voltage that passes through the entire circuit, that is also our reading in the other parallel uh, connection, okay, or parallel nodes. So VL divided by RL. Okay. So the same with Ohm's law, I is equal to V divided by R, wherein our voltage should be coming from the center voltage, and then RL or resistance should be coming from the load resistance. Okay, so that is why we have here an OR. IL is equal to VZ divided by RL because VZ is equal to VL. Okay, and then solving for the IS, the series current. So for you to be able to get the current here, so just basically it is the so actually you can do this one or do this one. So the easiest one is this one. Okay, IS equal to IZ plus IL. So if you're going to take a look at this one, this is our total current. Okay, wherein our current will be divided into two. So some currents will go here, and then some currents will go right here. Okay, so it's like division of two. So that is why we have this one. IS is equal to IZ plus IL. Or you can have this one. Okay, if let's say IL and then IZ is not given. So Vs minus Vz. So you have to get the voltage here. Okay. So it's like V sub A minus V sub B, or voltage source minus the uh, Zener, excuse me, Zener voltage. Okay. So that is why we have Vs minus Vz divided by the series resistance. Okay. So you have two ways to solve for the series resistance. And then for the PC, so same with our formula in powers, like P is equal to I times V. But in here, so for you to be able to get the power in Zener diode, so you have to get the voltage of Zener diode and then the current of the Zener diode also. So PZ is equal to VZ times IZ, okay, wherein VZ is our Zener voltage and then IZ is our Zener current. Okay. So for now, you don't need to memorize this one. Okay, just familiarize how to solve certain missing values. Okay. So for you to be able to appreciate this one, let's move on to the example. Right, so example number one, Zener diode as voltage regulator. So find the V out, current across load resistance, current across series resistance, current across Zener diode, and the power dissipated across Zener diode. Okay, so as you can see right here, we have a voltage source of 20 volts, we have a series resistance of 150, we have a load resistance of 1000, and then we have a Zener or a breakdown voltage of Zener diode of 8 volts. And then we have here node A and then node B. Okay, just to have an easier explanation that this one is a node A and this one is a node B. All right, so without a further delay, let me show to you the solution. Okay, so in here, I will only show to you guys the breakdown operating Zener voltage. So we will not show, or I will not show to you, okay, the conventional way of computing one, which is a forward bias. So we will only compute for the reverse bias. Okay, since we're using Zener, so this one should be working with reverse bias only. So the very first step that you need to do is check whether your V1 or voltage source is greater than the Zener diode, okay, or the voltage of the Zener. But for you to be able to get this one, the exact voltage of the V1, you have to deduct, okay, the voltage drop of the series resistance and then the load resistance. So for you to be able to do that one, you have to apply Thevenin's formula, okay, which is the VTH. So in here we have VTH is equal to V sub 1 times RL divided by RL plus RS. Okay, so just simply put their corresponding values. So V sub 1 is 20 volts times 1000, which is the RL, divided by 1000 plus 150 is the RL plus R sub S. Okay, so just do the math. So you can calculate this one first before multiplying it by 20. Then you will get 17.39 volts. So as you can see from 20, it became 17.39 volts because we've now deducted the voltage drop across series resistance and then the load resistance. Okay, so from here we can now compare VTH is greater than VZ. Okay, so we could now say that V out is equal to VZ because that's the only voltage across in this circuit. Okay, so whatever is the voltage drop of this diode will be our V out already. Okay, so as a result, since we have a center voltage of 8 volts, so our V out is 8 volts. Okay, so that is our first answer with this one by solving the V out. Next one is current across load resistance. Okay, so the formula for this one is VZ, okay, divided by RL, or initially this one is VL. Okay, VL divided by RL. But then again, whatever is the voltage across here in your VL is equal to your VZ because that is where our voltage drop is coming from. So we could say that VZ divided by RL, wherein VZ is 8 volts, okay, is 1, and then RL is 1 kiloohms. So just put that one in your calculator, then you will get 8 milliamps. Okay, so that is our current on the load resistance. Next one is the current for the series resistance. So from here, uh, so let's see if we can use this one, IZ plus IL. We have the IL, but we don't have the IZ yet at this point, okay? So we will be using this one instead, VS minus VZ divided by RS, okay? Or VA minus VB divided by RS. So why VA? Because at this point, what is our voltage? So our voltage from here is the VS, okay? And then VB is the voltage of the Zener diode, okay, which of course will pass to this diode. So from here, so VA is 20 and then VB is 8. So 20 minus 8 divided by, what is our RS? 150. So just do the math, then you will get 80 milliamps. So the current across this one, or the current that is passing this one, is 80 milliampere. And then again, for you to be able to get the IZ, so we have the formula IS is equal to IZ plus IL because our IS is the uh, total current. Okay, and then it will be divided into two. Well, not exactly divided into two, but some current will pass through here, and then some current will pass through here. So as you can see right here, just by using IS is equal to IZ plus IL, we've arrived with this formula wherein IZ is equal to IS minus IL, wherein IS is the 80 milliamps and then IL is negative, 8 only, not negative, 8 milliamps. So just solve that one and you will get 72 milliamps. Okay. And the last one is the power dissipated across the Zener diode. So again, it's the same formula with our power that we're using before. So P is equal to I times V. So for you to be able to get the power in Zener, so you have to get the current of the Zener and then the voltage of the Zener also. So just substitute their corresponding values wherein IZ is 72 milliamps and then VZ is 8 volts. So just do the math, then you will get 0.576 watts. All right, so that's how you solve for those values for IS, IL, IZ, and so on and so forth. Okay, so I'll give you guys a minute to analyze this one to understand further. And yeah, if you have a question or a clarification regarding with the solution, so feel free to ask anytime. And if it's clear, then let me know that it is clear to you guys on how we've got those answers, so that I just know that some of you get it. All right, so do you guys have a question so far or concern? So coming from Mr. Charles, so he says that it's clear. So that's good for you. How about the others?
Yeah, sure.
All right. Okay, clear. Coming from Mr. Escobar and Mr. Demondon. How about to you, Mr. Pacific? Did you get it so far?
Yes, sir. Good, sir.
Right, that's good. So coming from Mr. Waster and then Miss Kangat. So it is clear for them. All right, so it seems that most of you have understood it already. Okay, then, so that's good. So let's have this example number 2. Okay, so in some cases, okay, uh, let me just have a recap this one. So yes, it is easy to solve for the IS, IZ, and IL or any other missing variables if we have or if you have those values, like you have your VS, your RS, your Zener voltage, and so on and so forth. But in some cases, okay, we have a missing value in RL, we have a missing value of RS, we have a missing value of VS. So in here, we have to get the minimum load resistance wherein this Zener diode will still function under breakdown voltage. Okay, and then we will also solve for the maximum value of the RL wherein still the Zener breakdown voltage or this Zener diode will still work under as a Zener diode. Okay. So we only have two. Yeah, we only have two goals for this one. So solve for the RL min, which is the minimum, and then solve for the RL max, which is for the maximum. So as you can see right here, we have an additional current wherein the IZM. So IZM is the maximum current that can flow through a Zener diode, okay, at its rated Zener voltage. That is why we have to check whether the maximum RL will still be able to, work under the IZM, because if it's not, then we have to, lessen the RL. Okay, but don't worry, we have formulas for those missing variable RL. Okay, so without a further delay, let us now start on how to get the RL. All right, so solving for the RL minimum. Okay, so the formula for the RL minimum is RS times the Zener voltage divided by the voltage source minus the Zener voltage. Okay, so excuse me. So if those values or if those variables uh, are okay, so just put their corresponding values, substitute it. So RS is 100, okay? And then VZ is 5 volts divided by, so VS is 15 volts, and then VZ is negative 5 volts. So our minimum voltage is, minimum load resistance is 50 ohms, okay? Wherein this will still conduct, or it will still operate under a Zener breakdown voltage. Okay, and then solving for the RL max. Okay, so this one is actually uh, kinda longer to solve than the RL min. Okay, that is usually the case. So first, before you will able to solve for the RL max, you have to solve first, or you have to find the IS and the IL min first. Okay, so let's solve for the IS first, which is the current of our series resistance, or this one. So IS is equal to VA minus VB. Okay, so VA is this one, and then VB is this one. So as you can see right here, VA is 15 volts, and then our VB is 5 volts. All right. So 15 minus 5 divided by RS, which is 100. So 15 minus 5 divided by 100 is equal to 100 milliamps. So this is our current, okay, on our series resistance. And then solving for the IL min, okay. So IL min is equal to IS minus IZM. So IS is already being solved, and then IZM is the maximum current of the Zener diode. So IZM is equal to 25 milliamps. So just substitute the IS. So 100 milliamps minus 25 milliamps. So solve this one, then you will get 75 milliamps. Now we already have our IL min and then the IS. So now we can solve for the RL max. Okay. So the formula for RL max is equal to VZ, okay, the Zener voltage divided by the minimum, okay, current of our load resistance. So VZ is 5 volts, and then IL min is this one, which we have just solved a while ago, which is 75. So correction, this one is 75 milliamps. Okay, there should be an MA here, which is milliamps. Okay, so just solve this one. 5 divided by 75 milliamps, then you will get 66.67 ohms. Okay, so let me just write this one, so that I know that I have to change this one. Slide 15. All right. So our maximum load resistance that is allowed on the Zener diode is 100 milliamps. No. 50 ohms rather. Sorry, 50 ohms. Did I see RL max or RL minimum? Anyway, the RL minimum that is allowed on the Zener diode is 50 ohms. And then the RL max that is allowed on the Zener diode is 66.67 ohms, which will work under the breakdown voltage. Okay, so yeah, that's how we solve for those missing variables for the RL, mean and RL max. So yeah, memorizing those formulas is actually kind of difficult, but it's a good thing that, you know, it's an online distance learning, because if not, then you have to memorize those formulas. Okay. So for now, do you guys have a question or clarification so far regarding with the example number 2? None yet, sir. So none coming from Mr. Escobar, none coming from Mr. Ramos. Okay, that's a good thing. Okay, none coming from Mr. Pulmano, none coming from Mr. Nalaika. None coming from Mr. Charles, none coming from Mr. Eda. Alright, so seems that most of you doesn't have a question for now. So let's move on with our oops. Oh no. This one should be example number 3. So let me write this one down. Slide 16. All right. So in example number 2, we have RL as a variable. And then in example number 3, VS now is the variable. Okay. So we now have the value for the RL, but we now have a missing value for the VS. So in here, we're going to find the minimum voltage wherein it will still work under, Zener breakdown voltage. And then we're going to find the VS max, or the maximum voltage source, wherein it will still be accepted by the Zener diode voltage if it has a maximum current of 25 milliamps. Okay, so yeah, everything is still the same. Just yeah, 100 ohms in this one, still 100 ohms for our RS. Just a missing VS, and then now has a value for our RL. Alright, so without a further delay, let's discuss the solution for the example number 3. Okay, slide 17. Slide 17. Alright, so solving for the VS mean. Okay, so this one is actually super easy. This is the very first tip. So you have to solve for the minimum requirement first before going to the maximum, because solving the minimum is the easiest way for you to be able to uh, get an initial points or a correct points already, and then solve for the VS max once you're done with the VS mean or RS mean or IL mean or any minimum uh, missing variable. So solving for the VS mean, okay, so the formula for that one is equal to VZ times RS plus RL divided by RL. Okay, so RS is already given, RL is already also given, so just basically substitute those corresponding values in our formula. So VZ is 7, so RS is 100 plus RL is 300 divided by 300. Okay, so just do the math, then you will get this one, 9.33 volts. So the minimum voltage that will still be accepted, or which will make this Zener diode work under a Zener breakdown voltage is 9.33 volts. Okay, and then solving for the VS max. Okay, so again, before you will be able to solve for the VS max, you have to find the IL and then the IS max first. So solving for IL. So coming from the IS, no. So this is the other formula. So in here, solving for the IL minus VZ divided by RL. We have, no. So this one should be equal, okay? So correction again, not minus. This one should be equal. IL is equal to VZ divided by RL. So many corrections. Slide 17. All right. So again, this one is IL is equal to VZ divided by RL. So VZ is already given, which is this one, 7 volts. And then divided by RL is equal to 300. So 7 divided by 300 is equal to 23.33 milliamps. Okay. And then solving for the IS max. So IS max is equal to IZM plus IL. So IZM here is 25 milliamps, which is the maximum current of our Zener diode. And then IL is already solved, which is 23.33. So basically just put their corresponding values. So 25 milliamps plus 23.33 milliamps is equal to 48.33 milliamps. So that is our maximum current here, IS max. Okay. And then now, once we have those values, let's say you're now done with those two, that's the time that you can solve for the VS max. So we actually have this formula. IS max is equal to VS max minus VC divided by RS, wherein IS max is 48.33. VS max is the missing value that we're trying to solve. And then VZ is 7 volts, and then RS is 100 volts. So, just do the math, and then you will, or just simplify the equation first. Okay, so you will get this one once you simplify this equation. Okay, so just do the math from here. Yeah, 48.33 milliamps times 100, and whatever is the result of this one, just add 7. So just calculate this one, you will get 11.833 volts. So the minimum voltage is 9.33, and then the maximum voltage is 11.833. Right? So you can check this one later on once you have the time to verify whether the solution is correct or no. But for now, is this clear so far, guys? So correction, this one is IL is equal to, right? So question so far? So I'll count 5 seconds. 5, 4, 3, 2, and then 1. Right, so an answer coming from Mr. Eda. So we don't have enough time anymore. So we will continue the rest, okay, on the part 3. Okay. So actually we're almost done. Maybe the part 3 will only take 10 minutes, more or less. So goodbye for now, and then wait 5 to 7 minutes for the part 3. Okay. So I will end this one now so that I can convert the product card video as soon as possible. So goodbye for now, and then see you on the part 3.